All right, good morning, everyone. My name is Ibrahim. I'm going to be your presenter today for session two of the CCNA series. Today, what we're going to be going over mainly layer two of the OSI model. This is the data link layer. So this is where we're going to have, our switches. We're going to have a bunch of other protocols that I'm going to be explaining in depth as well. Um, uh, what we see here, these are the exam objectives. So this is 2.0. These are going to be all of the the protocols and things that we're going to be explaining. Um, First up on the list is going to be VLANs. But before we go into VLANs, let's go ahead and understand what a LAN is, right? So it stands for a local area network. And this is a collection of computers and network devices within a limited geographic area. So this could be anything like, your home, your office, or some sort of campus, right? They commonly use layer two switches to connect devices together. And this also includes all devices in the same broadcast domain. Now, what is a broadcast domain? What does that mean? So let's take a look at these pictures here. We have, let me go ahead and get this annotation here. A second. Cool. Oh, cool. So let's go and take a look at broadcast domain one here. So what's happening here is we have Dino and Fred that are connected to switch one. And if we look at broadcast domain two, we have Wilma and Betty who are connected to switch two. So what this means is, let's just say, for example, Dino wants to send out a broadcast message onto the network. By default, when a switch receives a broadcast message, what it's going to do is it's going to forward it out all of its ports, right? In this specific situation, it's going to go from Dino, directly to Fred because there's nobody else, actually on the network, right? So we can do the same thing with Wilma and Betty, right? Let's say Wilma sends out a broadcast message. The switch is going to send it out all of its ports, and the one who's going to receive it is Betty, right? Go ahead and go on to the next slide. Wait, 1 second. There we go. All right. So now let's move on to VLANs, right? So what a VLAN does is it segments a physical LAN into multiple isolated networks, even though they're connected to the same switch, right? Each of these isolated networks is its own broadcast domain. This also operates at layer two of the TCP/IP stack, or also layer two of the OSI model. So let's take a look at the photo here. This is a key topic. The only difference, this is pretty similar to what we were looking at before, but the difference now is that we have one switch instead of two, right? Dino and Fred are connected to switch one, and Wilma and Betty are connected to switch one. The difference here is what we did was we created a VLAN. We put Dino and Fred in their own VLAN, and then we put Wilma and Betty in their own VLAN as well. So that's VLAN one and VLAN two. So let's take that same hypothetical that we said in the last one, right? Where Dino is going to send out a broadcast message out on the network. Where do we think this is going to go, right? It's going to go directly to Fred. Why? Because each VLAN is its own broadcast domain, right? It's basically as if you have another switch within the switch, right? And then we can do the same thing as well for Wilma and Betty. Let's say Wilma wants to send out broadcast messages as well. It's going to go straight from Wilma to the switch and then directly to Betty. And the reason why, Dino and Fred don't see any of this is because they're on their own broadcast domain. Does that make sense, everyone? Any questions before I continue on? Cool. All right. So let's talk about the benefits of VLANs, right? So in this last one, we were talking about how this separates sensitive traffic, right? Since its own broadcast domain, right? This also, reduces CPU overhead and security risk by reducing the number of devices that receive each broadcast frame, right? This also improves network organization by grouping users logically instead of physically, right? And then it also reduces the workload for spanning tree protocol by reducing the number of ports STP needs to monitor for loops. Now, I know this is probably a new topic here with spanning tree protocol. We are going to explain this a little bit more in depth later on in this session. So don't worry about that too much, but these are some of the benefits of VLANs. So now let's go over the VLAN port types in 802.1q tagging. So with VLANs, there are two types of ports that you can have, right? You have an access port This is carrying traffic for only one VLAN. This is typically used for your end devices. So you'll see like your servers, your PCs, your laptops, printers, things like that, right? Um, but then some switches also allow the creation of the voice VLAN, which this only carries voice traffic. So if we see something, say like an IP phone or any sort of like phone device, right, that'll be connected to the voice VLAN. Now, for the second port, we have a trunk port. Now, this is carrying traffic for multiple VLANs using 802.1q tagging between switches. And now you guys are probably saying, whoa, well, what is 802.1q tag? And we haven't gone over that yet. If we think about what we went through in the last session with Dave, he was telling us a little bit about encapsulation, right? So 802.1q tagging, it basically adds a VLAN ID to Ethernet frames. And remember, this is layer 2 Ethernet frames. These are operating at layer 2. And this is indicating which VLAN the frame belongs to, right? This will only occur on trunk ports. 802.1q, it also defines one special VLAN ID on each trunk as the native VLAN, and this defaults to VLAN 1. Now, if a switch receives a frame with no VLAN tag, it assumes that that frame belongs to the native VLAN. So if that VLAN is 1, it'll just send it out to 1 if there's no tag on it. Let's take a look at the photo at the bottom as well. This is a key topic. What we're looking at here, this is just an Ethernet frame. And within that Ethernet frame, we have a destination address, source address, 802.1q tag, a type, data, and frame check sequence field, right? What I want you guys to take a look at is this 802.1q tag. Now, this is exactly what I was talking about. What it's including is a VLAN ID. This is 12 bits. And this is basically just identifying what VLAN that frame belongs to, right? So that VLAN ID might be VLAN 20, and it's telling the switch, hey, this belongs to VLAN 20. So send that over there, right? Any questions on that? Does that make sense? Cool.
Yeah, that makes sense. That makes sense. Let me ask you. So you said native VLAN. So and maybe you haven't got there yet, would that native VLAN, if it's traversing a trunk, would be tagged traffic or would it be untagged traffic?
So it'll be untagged, right?
Okay.
So what happens is 802.1q, what was that?
No, keep going. I'm sorry.
Oh, so 802.1q, what it's doing is, let's just say hypothetically, we have a frame that's destined for VLAN 20, right?
Okay.
The trunk that it has to traverse, it also has the native VLAN of, let's just say, 1, right?
Okay.
Because it's not the default, or because it's not the native VLAN 1, right? It's going to be tagged with that VLAN 20. Now, if it was destined for VLAN 1, then it would be untagged. The switch knows exactly what the native VLAN is. So if there is no tag on it, it's going to say, oh, I'm just going to send it straight to the native VLAN, which in this case, we'll say it's VLAN 1.
Got you. Okay. Okay. All right. That makes sense. And I'm sure you'll
Cool.
go over it more in depth within your lab session on Thursday and the practical lab. Okay. Thank you.
Yeah, absolutely. No problem. All right. So now let's take a look at multi-switch VLANs with trunking. Now, this might look a little bit like a lot, so I'm going to go ahead and annotate it a little bit. What we have here is we have 2 switches, right? Switch 1 and switch 2. And then we have 2 VLANs. We have VLAN 10 on switch 1 and switch 2. And then we have VLAN 20 on switch 1 and switch 2, right? So hypothetically, let's just say PC 11 sitting right here wants to send an Ethernet frame over to PC 13 or 14, right? Now, VLAN 10 is configured on both switch 1 and switch 2, but how do we get it over there, right? Because we were talking before about how the broadcast, we're just going to be sent out all the other switch ports that belong to that VLAN, but now it's on a different switch, right? So PC 11 is going to send its Ethernet frame directly to the switch, right? And the switch says, okay, well, I don't have any other ports that are, in VLAN 10, right? And let's just say it's destined for, of course, VLAN or PC 13 or 14. So what it's going to do is it's going to send it over what's called a trunk, right? This is the trunk. gig Ethernet 01. But let's remember what the trunk is doing, right? The trunk is carrying traffic for multiple VLANs. Think of this as like a highway, right? When you're on the highway, there's various different people. There's a lot of different, people that's on that highway, and they're destined for different areas, right? So this trunk, it can carry traffic from VLAN 10, VLAN 20. If we had VLAN 30, 40, whatever VLANs that are on here, right? So long as it's configured that way, right? Um, so step two, it's going to send this out of gig 01, but what it's going to do is it's going to tag it with that VLAN ID, right? Remember, this is 802.1q tagging. So it's going to tag it so that when switch 2 receives this Ethernet frame, it'll say, oh, I know that this belongs to, to VLAN 10. So we can just X out this VLAN 20 and like, because, it's VLAN 20, right? It's not VLAN 10. And we can send it directly over to wherever it's destined in VLAN 10, right? Oh, that was a bad one. In VLAN 10, right? Does that make sense so far?
Yes.
All good, all good. Cool. So let's do another example where we're gonna do it from VLAN 20 instead. But this time we're gonna do a broadcast message. And as we know with the broadcast messages, the switch is gonna send it out all of its switch ports, right? So let's say, all right, cool. PC21 wants to send out a broadcast message over to VLAN 20. The switch will take that and say, oh, okay, I see that, I have another port that's also in VLAN 20, which is 04. So it's going to send it directly over to PC22, right? But then another question is, how do we get it over to switch 2, who also has VLAN 20? We're going to traverse that same trunk, and it's going to go through that same process of it being tagged, right? So now instead of it being for VLAN 20, it'll be tagged with instead of it being tagged for VLAN 10, it's going to be tagged for VLAN 20. So that switch 2 knows, oh, okay, this is a broadcast message that's for VLAN 20, right? And that's how it'll get to PC 23 and PC 24, right? Moving on, we have inter-VLAN routing. So as we've explained, devices in different VLANs, they cannot communicate directly with each other. Now, this can be accomplished via what's called inter-VLAN routing. So to forward packets between VLANs, the network must use a device that either is a router or a device that acts as a router. And now you might say, okay, well, what is a device that acts as a router, right? So I'm going to introduce the concept of a layer 3 switch, or what is sometimes also called a multi-layer switch. So as we know, switches typically operate at layer 2 of the OSI model, right? And, if we take a look at what, layer 3 does, right? What are we doing on that layer, right? We're going to be doing, IP addressing, we're going to be doing IP routing, but what's going to be on there, right? It's mainly going to be routers. The whole purpose is so that we can route packets to where they need to be, right? And remember, this is layer 3 now. So let's go ahead and take a look at the diagram here. So very similar situation here. We have VLAN 10 and also subnet 10. This is something that we're going to cover in later series, but just for now, let's just say it's subnet 10. This is just a network, right? And then VLAN 20 and subnet 20, these are just two separate networks, right? Let's just think of it that way. So let's say in this situation, we want Fred to send an IP packet over to Betty. How does this work? Because we know that the VLANs, they can't communicate with each other, right? They're in two separate VLANs. So what Fred has to do is he has to send a layer 3 packet, right, over to this router, right? But let's remember what the router is doing. The router is meant to route packets between different networks. And we already know that, Dino, Fred, and Wilma and Betty, they're on two separate networks. So what the router is going to do is it's going to check through what's called its routing table. It's going to check for a route over to Betty, right? Basically saying, oh, I know where Betty lives, so I'm going to go ahead and route that packet over to Betty. And that's how we can accomplish communication between two different VLANs. It has to happen at the layer 3 level. Any questions? Cool.
Yeah, so you said something peculiar, which I loved, and I want to just to ride your coattails a little bit. I want to make sure everybody understands, right? So he stated, right? He used the term layer two VLANs, right? And he also used the term to define them as subnets as well, right? Right. And when we're talking about subnets and we're talking about IP routing, we're talking about layer three, right? He made an important point that I think I need you guys to understand, right? Traffic between VLANs at layer two cannot happen without a layer three boundary, right? So there needs to be a layer two instance, needs to be a layer three instance, and it needs to be that layer three boundary, right? Which is of course will be that router, that layer three device, whatever, right? That will pass that traffic, right? If not, traffic cannot traverse between one or the other, right? So please, for your CCNA exam, make sure you understand that, okay? And even for your interviews, your future technical interviews, because um, a lot of interviews now are going back to being super technical. Even though you're getting your CCNA, they're going to test you at the CCNP level for these interviews. Okay, so understand what he just broke down. I think that was a key part in your studies. Okay, thank you so much, Ib. Go ahead.
Thank you. Thank you. Moving on, we're going to layer two neighbor discovery protocols. So a discovery protocol, it helps devices share information about themselves with directly connected neighbors, right? Let's just say I'm sitting next to Dave, right? We're friends. We're going to exchange our information. He might give me his number. He's going to tell me his name. He's going to tell me information about himself, but I'm also going to do the same thing, right? Um, there's two main discovery protocols that we use. It's going to be Cisco Discovery Protocol, CDP, and then Link Layer Discovery Protocol. I'm going to go into CDP here and kind of give you a better idea of what kind of information is going to be exchanged between two network devices, right? So CDP, this operates at layer two of the OSI model or the TCP/IP stack. It is Cisco proprietary, so that means that this can only be used on Cisco devices, and it's also enabled by default on these Cisco devices. Now, I want to show you some output from a switch. The command is show CDP neighbors, right? And what we're going to look at is it's going to be giving us a lot of information about a directly connected neighbor. So we look at the device ID, right? It's going to tell us that we have switch two that's connected directly here. This is it's going to give us its host name, right? This is our identifier for that system. Under local interface, this is going to be the interface that's local to the switch. So if you see, we're on switch one. So this is connected to the fast Ethernet 09 on switch one, right? We also have the hold time. And this is basically the amount of time that the switch will hold this information before it's considered dead, right? If I don't hear anything from Dave in 138 seconds, I'm going to think he's dead. That sounds funny, but that's how it works, right? We also have the capability, right? Before we look at all these codes, let's look at where it says capability codes. So we have R for router. This is telling you that the device that's connected to you is a router. S for switch, D for remote, so on and so forth, right? The platform, this is basically just giving us the model of the devices connected. So you see this can be a Cisco 3560. That's the kind of switch that we have connected here. And then we also have what's called the port ID. This is the remote port. So this means that since we know that switch 2 is connected, right, this is the port that switch 2 is connected on. Any questions about that so far?
Yes, I do. May I actually know what is the max hold time?
The max hold time? I'm actually not sure. Dave, do you know what the max hold time is? Or
Max,
anyone on this call?
max hold time for the CDP neighbor table?
Yeah.
That's right.
I can't answer that at the moment, but I can go ahead and provide a article that can go ahead and give that to you.
Okay.
Yeah, for sure. And also any questions that we can't answer on the call immediately, you can go ahead and type that into the subject help chat in the Discord, and then we will answer that at a later date.
Okay, thank you.
Yep, no problem. On to the next one, we have link layer discovery protocol. This is very similar to CDP, but the main difference is that it is vendor neutral. What does that mean? That means that we can use it on various different vendors, like, okay, Juniper. We can use it on Arista. We can also use it on Cisco, right? But it gives you more flexibility in what devices you can use it on. Whereas with CDP, Cisco Discovery Protocol, this only can be used on Cisco devices. And then this is just some output from the show LLDP neighbors command. It's very similar to to the CDP command, so I'm not going to go too deep into that. Let's see. Moving on to EtherChannel. So EtherChannel, this is a technology that's used to bundle multiple physical links into a single logical link. So this is going to be combining the bandwidth, it's providing redundancy, and then load balancing as well. So before I go any further, let's go ahead and just take a look at this photo, right? So on switch 1, we have 2 ports. We have fast Ethernet 015 and 14. What we're going to be doing is we are taking these 2 physical links and we're combining them into what's called a channel group or a port channel. It can be used interchangeably. But this is basically going to be that logical port that's going to provide, all the bandwidth, the redundancy, load balancing. But how does that work, right? Let's say with the fast Ethernet 014, right? These ports typically have transfer speeds up 100 megabits per second. So if we combine both of those together, and then we create that logical port, right? Now we have a port channel that has 200 megabits per second, or that is capable of 200 megabits per second, right? We also said something about load balancing. So depending on the kind of traffic that's coming in, remember the channel group, this is strictly logical. The data is still going to be going through these 2 ports, right? But load balancing is just balancing the load between those 2 ports. Does that make sense?
Yeah, yeah, it makes sense. I got a question as well. So when you got the ether channel, whether it be running on a access switch or a core switch, right? Both links need to be forwarding so that traffic can traverse, right?
Right, right.
Okay.
Both of the ports have to be fully functional. We can't have a port that's down and it still be forwarding. However, what will happen though is, let's just say both of these ports are running right now, right? But we take port 14 out of the equation, right?
Mhm.
The channel group or the port channel is still going to be up. However, there's only going to be one available interface that's going to be forwarding traffic.
Got you.
Yes, sir.
That could potentially cause it to go down though, right? Because it's too much.
Yeah, if there's too much traffic on it, then it's possible that it could go down. So, you know, once you guys get into your networking roles, or if you're already in one, it's definitely important to be able to get these interfaces back up as quickly as possible, because we don't want to cause any sort of outage, right?
Got you. Appreciate it.
Yep, yep.
A question.
Yeah.
Thanks, IB. Can we use the like Ether channel port, Ether channels or LACP or LAGP, other than like switch to switch?
This typically will be used switch to switch. We can use it on layer 3, right?
Okay.
So this could be like a layer 3 switch to a layer 3 switch, right? Where we're also providing that routing capabilities, right?
Yeah. Is there a possibility we can use it with the voice gateways or like maybe servers that has like multiple Ethernet ports?
Like you said a voice gateway?
Yeah. So anything that has like more than one Ethernet port?
Well, it's possible to have redundancy. However, Ether channel is used between switches.
Okay.
So if I might jump in. So what he's saying is at its core level, if it's an Ethernet port and it runs 802.11, then it should be able to run LACP. Should be able to do that, right? Or PAGP, right? If it's not an Ethernet port, then it can't do that at its core level, right? So just understand what he's trying to tell you is it doesn't matter if it's a firewall, it doesn't matter if it's a voice gateway. If it runs 802.11 technologies, which run at layer 2, then it should be able to do ether channels or port channels. That makes sense? So don't get too
Understood.
focused. Don't get too focused on what a device is. Get focused on what protocols they can actually run, right? And of course, once you find out what protocols they can run, you can go ahead and confirm what specific technology they can do based on their data sheet, right? So if we're talking about Fortinet, right? Fortinets can do a port channel, right? Based on their data sheet, and they says, hey, we have this capability, right? And to reference how you would configure this, we have guides, and you can also look at the request for comments or the RFCs to look at how this works. Okay, that makes sense.
Yes, thank you.
But at a CCNA level, he is just letting you know what IB is letting you know at a core level, which is important for everybody to understand, because I think sometimes in the tech world we hear a lot of these buzzwords, we hear a lot of these high level technologies. Everybody forgets the fundamentals, so it ends up right. And in my case, we end up on a 4-hour call because everybody wants to throw out, hey, this is a voice gateway, this is a firewall, this is an SD-WAN gateway. When of course at the core level, dude, are these Ethernet ports or are they not? If they're not, then they can't do layer 2 functionality. If they're layer 3 ports, they're only doing layer 3. Boom, right? But do they have capabilities of 802.11? Do they do? Excellent. If they don't, excellent. This is what it can't do. So then you save a lot of the guesswork, right? Because you understand that theory, right? So again, this is why the CCNA is an amazing certification to go ahead and break a lot of this stuff down.
Thank you very much for clarifying it.
No problem. Go ahead,
Thanks for
IB.
jumping in there, Dave. Appreciate
No
you.
problem.
Appreciate you. Cool. So yes, it can be operated at layer 2 or layer 3. This is dependent upon configuration. And then we also have 2 protocols that can be used to configure a port channel, right, or ether channel, right? We have port aggregation protocol, and then we have link aggregation control protocol. With PAGP, this is a Cisco proprietary protocol, so this can only be used on Cisco devices. And with link aggregation control protocol, this is vendor neutral, so this can be used across multiple different vendors. Now let's take a look at the primary mission of a layer 2 switch, because soon we're going to be going into spanning tree. So let's figure out how these switches work. The ultimate goal of a layer 2 switch is to forward Ethernet frames, right? Switches receive Ethernet frames and then they make a switching decision. They'll either forward the frame or they'll ignore the frame. Now this is something from the book, so I'm going to go ahead and read this verbatim. But this is how a switch is supposed to accomplish these things, right? So it has to decide when to forward a frame or when to filter based on the destination MAC address. It has to prepare to forward frames by learning MAC addresses, by examining the source MAC address of each frame. And then it also prepares to forward only one copy of the frame to the destination by creating a layer 2 loop-free environment with other switches by using the spanning tree protocol. Now let's take a look at how frame switching works in action, right? So as we know, each individual device has its own, it's called a MAC address, or rather like a burned in address. This is your physical address, right? My computer has a physical address. All of your guys' computers have physical MAC addresses, right? So the way that this switch works is whenever, let's say Fred wants to send a destination frame over to Barney, right? What the switch is going to do is it's going to learn the source MAC address. It's going to learn Fred's MAC address and put it in what's called the MAC address table. This is also called the content addressable memory table, the CAM table. But what this is basically doing is it's giving us a binding of the MAC addresses over to the port that it connects on, right? So if we look at Fast Ethernet 01, we can look at the output of the MAC address table and say, oh, this is Fred's MAC address, and he connects on Fast Ethernet 01. The same thing will happen with Barney's MAC address, right? This is Barney's MAC address, and it shows that he's connected to Fast Ethernet 02. So the switch will learn the MAC address as data is passing through the network, right? And the switch learns it based off of source MAC address. Remember? Um, so let's go ahead and take a look here. So the frame came in on Fast Ethernet 01. Cool. It's destined over to Barney. Perfect. Barney gets it because it's destined for him. But what about the other ones? What about Wilma and Betty, right? Because the switch is already looking at its MAC address table and it knows where Barney is located, it's going to filter it, meaning it's not going to send it out to Wilma and Betty because the switch knows that it does not belong to Wilma or Betty, right? Does that make sense?
Yeah, it does.
Cool, cool.
Yes, it does.
We're kind of reinforcing this about learning MAC addresses. So let's go ahead and take a look up here. So this is the address table before any frame is sent out, right? It's completely empty, right? Now we're going to look at number 1 here. We're going to see that Fred is sending a frame down to Barney, right? Now let's also take a look at the MAC address table now. We see that we have the source address the source MAC address of Fred, right? And it says that he's also connected on Fast Ethernet 01. So it's learning as as the frames are being sent on the network, right? And then the same thing will happen with Barney. When Barney wants to send a message over to Fred, the switch is going to take his source MAC address, and then it's going to add it into the MAC address table. And this is how all the bindings are created. It's really dependent on how much data is passing through the network, and it's going to identify what the MAC address is of that sending device, right? It's going to populate the MAC address table with that information. All right. Now moving on. Why do we need STP? This stands for the Spanning Tree Protocol. This is a layer 2 protocol that prevents loops in multiple switch topologies by blocking redundant paths. So what we see in this picture here, I'm going to show you what a loop looks like and how it works. So Larry, he has a frame that's destined for Bob, right? However, Bob is powered off. So his MAC address, it might have been there at some point in the MAC address table, but it's not there anymore. So Larry, he'll send out his frame, right? It'll go over to this switch 1, right? And switch 1's going to say, oh, well, I don't have I don't have Bob's MAC address in my MAC address table. So I'm going to send it out all of my ports, right? So we're going to send it up here. We're going to send it this way as well. And it's going to reach both of these switches. Now, both of these switches are also going to do the same thing and say, oh, well, I also don't know where Bob is located. So we're just going to keep sending it out until somebody figures it out, right? But we know since it's not in the table at all, no one's going to figure it out. And Bob's never going to respond because he's not even online, right? So this is what the loop looks like. It's basically just going to infinitely loop all of these frames because they're trying to figure out where Bob is and they can't figure it out. And that's going to cause a lot of congestion. It's going to slow down the network a lot because there's just a lot of unnecessary noise that's kind of coming on the network, right? But what we're going to explain is how spanning tree prevents this, right? 1 second here. All right, cool. Oh, there we go. All right, so let's explain what bridge protocol data units are. So BPDUs, these are standard STP messages. These are exchanged between switches, which identify their bridge ID, their root bridge ID, and cost to the root. So I know these are all new words. What is the root? Think of the root as like the king of the network, right? All decisions about what paths to use, are based off of how far each switch is from the root, right? The bridge ID, this consists of 2 parts. This is the bridge priority, which is a configurable value. Our default is 32,768. And then it's also based off of the MAC address as well, right? So this information within this BPDU is used to elect what's called a root bridge. Now, The root bridge basically is just the root switch, right? Now, how do we get that root switch, right? The switch with the lowest bridge ID, which if we remember is the priority plus the MAC address, will win, right? Now, all of the switches, they're going to calculate the best path to the root based on their link speed, right? And we see a picture here. This is also the spanning tree protocol bridge ID. So just letting you know, hey, this is the priority as well as the MAC address. And then let's take a look at port roles in spanning tree protocol. So in the basic spanning tree, we have three port roles. We have the root port, which is the best path to the root bridge. Remember, that's basically just the root switch, the king of the network. We have the designated port, which is the best forwarding port on a segment. And then we have our blocked port, which is the backup path to avoid loops. So I'm going to go back just a little bit because I want to talk a little bit about the blocked port. Do we remember when we were talking about the loop, right? You know, how it's just going to keep going around and around and around until I guess until the network dies, right? But what spanning tree is going to do is going to block one of these ports. Let's say it's going to block this port, right? So that we're establishing one flow of data, right? There's no need to have like a bunch of, redundant paths because, we have one trusted path that is not going to create a loop. And then we also have port states, right? So in basic spanning tree, there are 5 port states. We have blocking. This is going to prevent loops by not forwarding any user traffic at all. We have listening. This does not forward frames or learn any MAC addresses. It's simply just listening to the BPDUs, right? It's listening to that information about all the other switches to see which one will be the root switch, right? When we're in learning, it's learning MAC addresses to populate the CAM table or the MAC address table, and it doesn't forward traffic. And then we have forwarding, right? This is a fully active interface, and it's also forwarding user traffic. So this will be the normal operational state for working ports in the spanning tree protocol. And then we have the disabled port. This is where the port is shut down and it does not participate in the spanning tree protocol at all. Now, I want to go over some of the challenges with spanning tree protocol. It has a slow convergence time. What is convergence time, right? These are basically all the port changes, right, that go into effect. This is what we were talking about before with the different port states, right? It has to go through each of these port states to be able to get to that forwarding state. But it takes it a little while, right? It'll take it between 30 and 50 seconds for port changes to go into effect. What solves that issue? We have something called the Rapid Spanning Tree Protocol. This is defined by 802.1w. This solves it by reducing the convergence times, right? So it's definitely not going to be 30 to 50 seconds for it to converge, right? I'm not going to go too deep into rapid spanning tree and the other kinds of spanning trees. What I want for you guys right now is just to be able to understand the basics of spanning tree, and then once we get into the lab, we'll start to go a little bit deeper into into how the rest of that stuff works through configuration. And that's basically all that I have for now, guys. What I would like to do, if we want to have a bit of like an open discussion about all the things that we've kind of discussed, we can go ahead and do that. If anyone has any questions, we can just chat about it. What do you guys think?
That's good to me. Thank you, IB. That was really nice.
I'm with that for sure.
Session.
Yeah, we can do that.
Right back off that, I do have a question for you.
Yeah.
Or for actually the group. When we say the network dies, there is a loop. Can we go back to the slide? We understand like there is a broadcast stream and network dies at some point. Can we just actually get those points when it dies? Like how?
Like how can we identify when a broadcast storm is happening?
It's more of like there is, we know there is a broadcast storm happening. What would be the reasons like a network to be die? Obviously, broadcast storm is one, but what does it do to make the network die?
Oh, it's causing congestion. So let's think about how we have. Well, we're gonna discuss this in a later one, but basically, um, there's only so much that a port can handle, right? So if it's
Yeah.
taking in more, traffic than it can handle, things might happen where, let's just say, it's going to start dropping traffic, or the port might go down, right? So that's going to cause congestion in our network, and the traffic that we need to be forwarded or routed, it's not gonna happen.
Okay.
Now there are things we haven't gone over it, but there are things called like storm control, right? And what that's doing is it's going to set a threshold on an interface where if we have the utilization for it going up super high because of the broadcast storm, then it'll you can set it so that it can either shut the interface off, or it can just drop that extra traffic that's kind of coming in on that port. So there's definitely ways to avoid it, but yeah. Any other questions, guys?
Yeah, I have
So
one.
can you guys hear me?
Oh, go ahead.
We
My
can hear
bad.
you now. Yep.
Okay. I want to go back to Bashi's question, right? As far as how would we indicate, how we know a broadcast storm is happening, right? First things first, frames, right? Because we're talking about layer 2, right? When we talk about broadcast storms, right? They won't be traversing, right? So your end users or yourself would see, an outage. It'll be a known outage that you'll be able to see, right? So how can you verify that something is not going on at layer 2, right? What the broadcast storm is doing, exactly what IB said, is that the broadcast storm is sending so much frames, right, to the switch, and more specifically, right, I'm going to use some higher level terms. We're going to talk more in depth about this in later chapters, but we're going to go, really low levels right here, right? So the CPU is receiving so many frames on multiple interfaces, redundant interfaces, coming from the same source, right? To the point to where it's sending it back out on different ports and the same ports that it received the frames, right? And if every switch within that topology, within the tree, is doing that, right? Every switch within the topology CPU at its control plane is processing that and sending out instructions to the data plane and saying, hey, based on what I received, here are the instructions I want you to follow, right, to go ahead and forward this frame out, right? And it'll go ahead and look at its forwarding information base, and then go ahead and send it out, right? So now it's doing that at a high rate, right? It's doing that at a high rate to the point to where the amount of traffic that's ingressing, right? Ingressing and egressing the interfaces, right? The CPU can't even function properly, right? So now the CPU utilization is above 50%, right, during this broadcast storm, to the point to where if DeMarco tries to log into a switch during a broadcast storm, right, he can plug in via console cable, right, or he can use the way that he configured, which is SSH or Telnet, right, or any remote protocol, right. It won't be able to process it. It just won't, right? Let's say he plugs in via console. It's not going to work. The CPU can simply not process the request. It's similar to how if you have a PC with a low amount of RAM and you're trying to play Marvel Rivals on it, you try to use it as a gaming PC, it's just going to stop. It can't process. It doesn't have the power, right? So the broadcast storm is giving the switch too many things to do to the point where it can't process, right? So if we have, right, using the Dijkstra algorithm, right, the shortest path first algorithm, if we have that in place, right, to say, hey, find the shortest path, And also, because remember, IB talked about the 3 major functions of a layer 2 switch, which is important for the exam, right? One of the key functions is I am going to implement loop prevention, right? So I'm going to create a loop-free environment, right? So frames traverse only in one direction, not in multiple directions, to the point where we create a loop, right? And that's the issue that whenever networks were created back in the 1980s, that they had, right? And that's why we had collision domains, right? To the point where people had to wait to talk, right, on the network. So now we have switches, right? And now each interface is a collision domain, right? So we took care of that, but now we need to make sure that we instruct these interfaces that plug into different switches to say, hey, we have one way of getting, right, to our router, right, through these multiple switches of our, in our environment. We don't need to go multiple ways to the router. We just need one way, right? So we can have a loop-free, topology, right? Hopefully that answers your question.
It does. Thank you very much.
No problem.
David.
Thanks for the explanation, Dave. Really good, really good.
Thank you. Thank you, Dave.
All right. Anybody else?
Yeah, I had a question. So rapid spanning tree and rapid spanning tree plus, do they operate at the same level? Or I know it's a plus there, but do they kind of like operate at the same level, or one is
Same
kind
level
of
as in like the layer of the OSI model?
uh I'm meaning like the protocol, the rapid spanning tree protocol, rapid spanning tree protocol and the rapid spanning tree protocol plus. What I'm asking is like, I guess like what would be like the difference? Because just me reading, they both seem like similar.
Right. So let's take a look at this at the challenges, right? So the problem with the regular spanning tree is that it has a very slow convergence time. Let's say you get on your computer, right? And it takes you like a full minute to be able to actually send traffic. That takes a long time, right?
Right.
So these so rapid spanning tree protocol, this was created so that the ports don't have to wait so long to be able to forward traffic. It's about creating efficiency, right?
Gotcha. So it's just a way better, quicker convergence time.
Basically, yes. Yes.
Gotcha. Okay. Thank you.
Yes, sir.
I have a follow-up question from the broadcast room. And so situation. So if we are experiencing lag in the switch when we logged in, let's say broadcast roam is not that bad, would it be a broadcast roam be one of the reason that is actually creating a lag, like when we logged in, like SSH into a switch from remote?
So that question, which is very peculiar, it all depends, right? You can't. So within the CompTIA A+, right? You follow me? They
I do.
have this term called a troubleshooting methodology, which I love, right? And the thing about the troubleshooting methodology is that it has 7 steps, right? And correct me if I'm wrong, guys. Keep me honest here. I may be wrong. It's been a while. But between the middle of the process, they have a flow chart to where it says, hey, create a theory, test the theory. Is the theory right? Yes or no? If it's not, go back to the step, right? Maybe step 2, step 3, whereas you're creating a theory, right? Whenever you're troubleshooting anything within networking, within cybersecurity, within the cloud, this is the methodology you have to use to go ahead and troubleshoot something, right? Because there's never any absolutes whenever we're having issues in a non-working state, right? So it's up to you as a network engineer, right? Or the cloud engineer or the cybersecurity engineer to be able to have that skill of following the troubleshooting methodology and having the knowledge to say, I need to check all things at the different layers in the OSI model, right? Layer 1, layer 2, layer 3, layer 4, layer 5, layer 6, layer 7, right? I'm checking all these things, right? 3 times, 4 times if I have to find out what the issue is, right? There's so many things so many protocols and things that exist at every layer. You can't just say, oh, if I can't log into the switch, maybe it's because I have a broadcast. Maybe it's because SSH and Telnet, if you're trying to remote into it, if you're trying to connect to it remotely, right, it's disabled. And maybe you have to get into the switch, right? So this is going to take time and knowledge for you to gain over time on combining with the troubleshooting methodology to find out what issues are within different environments. Does that make sense?
Yes, it does. Yes, it does. Thank you.
If anybody else wants to add on, because I know a lot of you guys work in a troubleshooting role or what have you, feel free to chime in.
Great questions and answers. I love it.
I just have a question going back to, can you guys hear me?
Yeah, we can hear you.
Yeah, I just have a question going back to VLANs, right? So I guess my question is just kind of like reinforce how VLANs interact with each other on different switches. If a VLAN on one switch, let's just say a PC that's in a VLAN 10 on one switch 1, it sends out a broadcast, right? Oh, if it sends out a broadcast, and if switch 1 has a trunk link to switch 2, which also has VLAN 10. If PC 1 on VLAN 10 sends another, wants to send a broadcast, or it sends a broadcast, right? Would it just send that broadcast out to the members in VLAN 10, or does it send it out to all VLANs that are configured on that switch?
That's a good question. So let's remember that each VLAN is its own broadcast domain, right? So if you remember what a broadcast domain is, this is basically just the group of people who will the group of systems that will only receive this broadcast, right? So the answer to your question, if PC 11 sends a broadcast in VLAN 10, it'll only go out to VLAN 10. It won't go out to VLAN 20 or VLAN 30, or what have you, because they're in their own separate broadcast domain.
Okay, got it. Thank you.
Yep. Anything else, guys?
I do have a question about the VLANs. If anyone else has a question, they can go for it too. I might just be taking too much of your time. But my question is actually regarding the native VLAN and the access ports. I know like to provision a port, let's say for a VLAN 10 that actually connects, switch port connects to a PC that we need actually on a VLAN 10. I believe we use like we put the port on the access. I'm coming from a world where we have a HP, like old ProCurve switches. They go by tagging and untagging. This might just be a little bit different than we are studying, but I just want to get a little bit more understanding so that my understanding actually I can take it to any vendor, like have the core understanding of VLANs. I want to make sure I understand native VLAN versus the access port, or the VLAN, like a tag VLAN. Like what is tag and native and like we have an untag? Yeah.
So I got you. And I'm familiar with the Pro curves, right? Before HP went into Aruba, right? So I get what you're coming from, right?
Thank you.
IB is going to cover that, right, in a future session, right? Along with myself and a couple of others, right, in this group, right? But I'll give you a snippet, right? So, and I'll answer it in pieces, right? You said, how would there be a native VLAN on an access port? There would not be. An access port would be assigned to a VLAN. That's it. A native VLAN would only exist within a trunk. Because remember, a trunk is meant to traverse multiple VLANs. Make sense?
Okay.
Make
Yes.
sense? So
Yeah.
within, right, going back to what IB said, right? If we're talking about trunks, right, we can traverse multiple VLANs, right, within that port, right? That means for the frames that are traversing that port, it's going to be, right, notated with a specific number, right, a VLAN ID, right, as you can see right here, right, 1 through, 4094, right? It's been a while.
Yes.
Right?
That's right.
So it's going to be tagged with that type of number, right? All that traffic, right? Every frame is going to be tagged. Okay? Right?
Okay.
But for a trunk, there needs to be an identifier that says, what is the VLAN that is going to be dedicated to traffic that's going to be untagged, right? Because you can have untagged traffic and it not be the native, right? But what traffic is going to be untagged and also the native, right? And that's what you configure, right? And untagged is exactly what it means. It doesn't have a VLAN ID on it for that traffic, right?
Okay.
For the trunk. So it agrees, right? So if I create a trunk on my side, IB creates a trunk on his side. Let's say that native VLAN is VLAN 1000. That means if I'm sending traffic on VLAN 1, on VLAN 2, 3, 4, 5, and 6, all of that is going to be tagged. If we agreed that VLAN 1000 is going to be my native VLAN, that native VLAN traffic is going to be untagged, right? There's going to be a VLAN ID on it. But the switch, right, the control plane within both switches is going to know, hey, I'm going to read this as VLAN 1000 because it doesn't have a tag on it. Make sense?
It does. I was clear on the VLAN concept before joining the role. It was just like, so for example, where I come from, why I got more confused. So for example, like when we assign a port to the VLAN 10, so the computer can talk to that VLAN, right? Let's say it's a production VLAN. The command we used in the Aruba, in the HP ProCurve was like untagged VLAN 10. When it says untagged, then to me, that basically is a native VLAN. But
I see what you're saying, right? So, right, to go even further with my example, right, you can mark, right, on all vendors, VLANs within a trunk that are not the native, but are untagged. Here's what I mean by that, okay? So, let's say, right, IB was talking about the voice VLAN earlier, right?
Yes.
And there's a command to identify all of our, right? We have an architecture, right? And let's say we create that architecture that says, hey, our layer 3 switch is going to hand out IP addresses, right, to our phones for our phone and voice VLAN, okay? But how can we accomplish that? We can accomplish that by, right, creating, right, using the OUI commands, right? The voice VLAN commands within most switches, right? Every switch has it. It can be called something different, right? But we can configure every switch, right, to say, hey, if you see the first 6, characters within a MAC address, this is meant for the voice VLAN, right? Right. So because we're talking about layer 2, right? And stay with me on this example. Don't be too honed in on the voice, right? So if I have the OUI configured on this switch, right? And I say on the interface, right? And I say, hey, voice VLAN on this interface, on interface gigabit 0/1. That means if I have a PC connected to a phone and that phone connected to the switch, right? I'm going to go ahead, right, And that traffic, right? Because of course, the first thing the phone is going to do is request for power, right? If you don't normally, if we don't have a power source plugged in, it's going to receive power from the switch, right? So the PoE messages are going to traverse back and forth, right? They're going to negotiate on how much power is needed. Then boom, the phone's going to power up, right? The phone is also a host on the network, right? And for it to be a host on the network, it needs an IP address so that it can communicate. Before it can do that, right? It needs to get that, right? So DeMarco configures his switch for DHCP, right? But that port isn't a trunk port. So how is it going to identify the user VLAN and the voice VLAN? The way it's going to do that is because both VLANs are going to be untagged on that access. Okay?
Okay.
Right? And so that OUI command is going to say, hey, it's untagged, but I recognize this MAC address, the first 6 characters of this MAC address. Right? So even though this is untagged, there's different markers that has a use for this. So it's untagged, but I'm going to give you, right, that IP address in your VLAN because I know what this means, right, for this function, right? So you'll have an untagged VLAN for several reasons on a access port and a trunk port, right? It's not just the native, but at the core level for tagged and untagged. Untagged, it doesn't have a VLAN ID on it whenever traversing a trunk. Tagged, it does. That's it, right? And I think whenever we go through the practical, right, and we look at packet captures, you'll see what I mean. And I think combining that with an architectural design, it'll make sense to you versus just troubleshooting it. Does it make sense?
It does now. Although I learned the way how I need to work on the current switches, it actually did give me a lot of imposter syndrome when I joined this role because I was like, do I not even know the VLANs? But I would love to see a practical lab. I get it now, and I mean I was able to understand it.
Yeah.
But it still doesn't basically. I think maybe it's the wordings that it's just the wordings that the switches use. Yeah.
Mm-hmm. Yeah, it doesn't make sense. And again, it's not your fault that you got that they hired you. They hired you expecting that you would learn, right?
Yes.
So that's perfectly fine if you don't know, right? But this is where the CCNA comes in. You have to learn the terminology. So that's why a lot of the words that IB was going over today, it's very important to understand.
Okay. Thanks, David. Yeah.
No problem. Sorry, IB, go ahead.
No, it's all good. It's all good. Do we want to take one more question and go ahead and wrap it up? What do you guys think?
Everybody good?
Yeah.
All right, guys. I think we're done. Oh, Marquita, go ahead.
Oh no, I just said I'm good. This is a really good session. But
Awesome.
I would like to see this labbed if possible. If not, then I'd go YouTube, I guess. That's fine.
Yeah, of course. We're going to be doing the lab. Dave, remind me, is the lab going to be this Thursday or the next Thursday?
Yeah, it'll be this Thursday at 9:30.
All right. So that's the 10th, guys. So we'll be going over all this stuff in the actual lab, get the practical experience and all that. And this will definitely make a lot more sense once we get into the system and we're actually able to look at it. But thank you guys for joining, and we will see you guys again on Thursday.
Already.
Thank you. I appreciate it.
Bye.
All right, guys.
Have a good one.
Bye now.